Okay, in this segment, we're going to talk about where do SNPs come from, or whence SNPs. And this will be useful because it'll give a sense of population genetics, which we'll be talking about in future segments. So the first two things to remind you of is we have two basic processes that we've talked about a little bit, at least one of them. Mutation, which is when we get new variations arise because of random events in replication or from radiation exposure, but we have new variations. So that's one idea we will be using. And the other thing which I want to remind you of is recombination, an important phenomenon. So recombination is the idea that you get a chromosome from mom and from dad, but those chromosomes are specially made for you in the sense that mom got a chromosome from her mom and her dad, grandparents, and when she's making her eggs, and analogously when dad is making his sperm, they don't just give you one of their chromosomes. They actually take little pieces of both their mom and their dad to create a new chromosome. So let's say we have grandmom and granddad. Grandmom is a line as a genome. Granddad is just a squiggly line. This is your maternal grandmother and grandfather. When mom's eggs are being made, they take each chromosome, breaks up, and mixes pieces together so that the chromosome, for example, if this is what grandma gave mom, and this is what grandpa gave mom, what you might get, for example, is something like this. So this is the recombination event, which has literally recombined pieces of DNA to create two new chromosomes that were actually never present in grandma or grandpa, but are now present in mom's eggs. And so there's one egg, and there's another egg. This leads to good diversity because we can then mix and match and generate new humans that are not clones of each other. Same thing happens for sperm. And that's an important process because then we're going to see genes that perhaps never traveled together because they were in granddad or grandmom. Now they're traveling together because they've been mixed up. So we're going to use those ideas when we talk about where SNPs arise from. In general, just to say about combination, there are something less than 100 recombinations for every new genome. So if I look at all the chromosomes, the 23 chromosomes, and I look at all the recombinations, there'll be like 3 or 4 recombinations per chromosome. So in this case, we have 2 breaks, 1, 2. And in fact, for chromosomes in practice, it's about 2 to 5 recombinations per chromosome and a total of about 100 recombinations. So it's not millions of recombinations per generation, but there is some mixing. And that'll add up to 2 to 5 or maybe 10 breaks per chromosome, where a break is where it goes from a straight line to a squiggly line in my little example. Okay, so now let's think about the evolution of the human race. And we're going to go back to Africa 150,000 years ago. 150,000 years ago, YA. And there's a small group of humans. They're not taking many drugs. They're probably eating a lot of stuff from the wild. But let's say that on one segment of DNA, they basically all have a G, an A, and a T at these 3 positions. So there's N humans. They all, at least in this loci, and I haven't really told you how big it is, but I'm telling you that there's one location with a G, one with an A, and one with a T, and there's stuff in between that I'm not mentioning. Okay, that's great. That's our small little band of humans 150,000 years ago. Then a mutation happens. So somebody is having a baby, and that baby, through whatever reasoning, gets a mutation of this G to a T. So the new human has a T, A, T. This is new. So there's one of those, one little baby, plus the rest of the population still has GAT. It's about N still, okay? Now, there's a couple of things that can happen. This baby could get eaten by a lion, in which case this baby will not reproduce and we will never see that T ever again. Or this baby could have one baby and that baby gets eaten by a lion and we never see the T. You get the idea. We could never see the T if that baby is not reproductively successful. But let's take the happier thought that this baby has several other babies themselves, and that their babies have grandchildren and great-grandchildren, and that over time, time passes, and we actually have a population with a bunch of people who have TAT, let's say M of them, and then of course the original chromosome is still floating around. So just to use some of the vocabulary that we've learned in other segments, these are haplotypes. We created a new haplotype. The haplotype could have died out, but in this case it didn't die out. It started out as a mutation because it was rare and it was new. Now time has passed, it's no longer new, it's no longer that rare, there's N of them. I haven't told you what N is, but it's much bigger than 1. And so now it's a polymorphism, okay? And we have our first SNP, in this region at least, we have a TG SNP at position 1. Great, no problem. In fact, going great. But now we're going to say, well, somebody in this population has a new mutation. So another mutation happens. And this is going to be a mutation. I just want to make sure I get it right. In the third one, where it's a TAC. And then, of course, you still have TAT. And you still have GAT. So let me just bring you up to speed about what's going on here. So one of those people, one of those M people with the TAT had a baby, but during the process of making the baby and replicating their DNA, we got a new mutation, just like what happened up here. Okay, it's going to be the same story. And so at the time of the mutation, there's one of these, there's still about M of these, there's still about N of those, let's say. Everything is fine. Same thing. This may die out and we never see it. It may be a mutation and it never becomes a polymorphism. But the interesting case is that it becomes a polymorphism, in which case time passes. So we'll go over to this next column. So time passes from the second mutation. This is the C mutation, just to remind you where we are here. And we're going to have these 3 haplotypes floating around. You get the idea. I just want to make sure I get them right. I might actually reorder them. No, we're OK. TAC, TAT, GAT. And now there's non-trivial amounts of all of them. So GAT still has about M of them. TAT still has N. Sorry. TAT has M, and this one has P. So this was a successful, and the C has become a polymorphism. So bear with me. Now things are interesting. So we have a TG polymorphism, TG SNP, that's floating around in the population. That is to say there's a locus in the population where there are 2 alleles, T and G. This loci, we've only seen, this locus, we've only seen 1 allele. It's always been A. Nothing has happened yet. And here we have a CT SNP as well. But I want you to notice something about these SNPs at position 1 and 3. We'll call these positions 1, 2, and 3. What I want you to notice is that if I tell you that I've measured this SNP in an individual and it's a C, then you do not need to measure the SNP at position 1 because it has to be a T. That C arose on the TAT background. And so we've never seen a C at position 3 with a G at position 1. So knowledge of this allele, that is to say if it's a C, tells you that number 1 must be a T. Now, if I tell you that it's a T at position 3, you don't know for sure if it's going to be a T or a G. But the key point here, and in fact it's so key I'm going to write it out. is that knowledge of the allele at one position, in this case position 3, gives information, really probabilities, about the likely or perhaps definite allele at a different position. Okay, and in particular, just to repeat myself, knowledge that it's a C means you have a T. Now, I've given this long story about evolution in the context of SNPs, but this could happen for any variation that has arisen any time in the development of the human population. So I'm using SNPs because we talk about them the most, but this could be indels, this could be copy number variants. Any variation that you can count, alleles, could be connected to another variation because of this process of arising on a certain background and therefore having a connection. And this leads to a very important concept called, and it's unfortunately named, and I apologize for that, linkage disequilibrium, or LD. So LD is actually defined right above it. It's the knowledge of an allele at one position gives information about the likely allele at a different position. Two alleles, so it kind of begs the question of what would linkage equilibrium mean? I have never heard anybody talk about linkage equilibrium, but that would be a case where the two positions are unrelated and knowledge of one gives no information about the other. So no transferable knowledge from allele to allele. So for example, to go back to before we had this C mutation, we could have looked over here where we had a T and a G, and knowledge of a T at position 3 really gave you no information whatsoever about a T or a G. It was only the subsequent mutations and then polymorphisms that allowed us to get this phenomenon of information. So linkage disequilibrium is a very important concept in all of genetics because a lot of times we'll be measuring one SNP and that will often give us information about the likely alleles of other SNPs. Okay, but we're not done. I've done a lot of mutation, but I haven't done any recombination. So now I want to consider the impact of recombination. So every generation, there's a possibility that these haplotypes will be recombined. These are just like what we're getting from mom and dad. And so let me put it to you that we have now a recombination event. So some of these, everybody has 2 of these, by the way. There's 3 haplotypes floating around the population. We get one from mom, one from dad. So you can have people who are who have 2 copies of this, 2 copies of this, 2 copies of this, or one of this, one of this, one of that, any combination. All right. Let's say we have a combination between the GAT and the TAC. So we have a GAT and TAC individual. This is like a mom or a dad making an egg or a sperm. But they're doing a recombination, and they're doing the recombination here. Okay, so that's my symbol for a recombination, which means that the let's say the eggs that they're making are going to have GAC, and another one will have TAT. Now, we've seen TAT before, sort of over here, but we've never seen a GAC before. So that recombination event has created a new haplotype. So it's a new haplotype. More importantly, or as importantly, it has now ruined the perfect correlation between observing a C and predicting a T. Because now you have at least one individual for whom, when you see the C, it doesn't mean that they have a T at position 1. So this erodes the LD. That's what I'm going to call it. Whereas the LD was perfect. Perfect linkage disequilibrium means perfect predictability. Now, it still might be statistically more probable that you get a T when you see a C, but it's not a certainty. So let's think. So hopefully that's clear, that we're eroding the correlation. And the more recombinations that happen, so more recombinations means more erosion. And in fact, if you have a ton of recombinations mixing up this little triple of loci, eventually you can get no LD, which means there's no information about one allele given the other. Okay. Let's think about under what circumstances would that happen. And it's related to the distance between these bases. I've drawn them here with no scale. I didn't tell you if G to T is 100 base pairs, and there's 40 here and 60 there, or if this is 1,000,000 base pairs, because I just didn't label it. But that's now critical. If it's 100, and if I have 30 to 100 recombinations per generation, this will survive for many, many generations without ever having the kind of unlucky event of a recombination in this stretch of 40 or 50 bases. And therefore, the LD between this guy and this guy will remain intact for long, long periods of time, many, many generations. If, however, it's 1,000,000 base pairs, then over time it is very likely that I will have not just one but many recombinations, and so that at large distances, LD erodes more quickly. So LD erodes faster for distant loci. What's cool about that is if you can measure the connection between two SNPs, you can estimate how far apart they are in the genome, making assumptions about the rate of recombination, et cetera. It also means that for different populations that are different ages, and we'll talk about this in another segment soon, you can use LD to estimate how old a population is and whether it's relatively recent with a lot of common ancestors or if it's an ancient population that's been doing recombination for a long time. Just a few things to finish up. LD, there are many measures of LD, and I'm not going to go into the details of this, but one famous one is called D prime, which goes from 0 to 1. 1 means perfect predictability of the alleles given the knowledge of the other alleles, and 0 means no information given knowledge of the other allele. Another important thing is we're going to be talking about discovery of genetic variants responsible for traits in the human genome. If these two columns are in high LD, then you can't tell. So if they're in high LD, that means they're very correlated. If there's a disease that this SNP is correlated with, and we'll talk about this later, you can't tell if it's correlated to the disease because it's directly related to the disease or because this guy is directly related to the disease and this guy is just correlated with this guy. Now, I'm not explaining that idea in detail, but I hope you hold that thought because in future segments, we'll talk about the impact of LD on discovering genetic associations. And I'll end up just stressing that although all of these examples were shown for SNPs arising in the population, the mutations that I discussed here could be other types of mutations, and the same principles of mutation turning into polymorphism and then having statistical linkage through linkage disequilibrium are all valid, and the erosion of that based on the distance between those variations is also a very general concept not limited to SNPs.